In this video, I want to talk to you about color coding in a circuit and use that to derive an equation. And so what you'll see is that I've got a battery and 4 round bulbs in series, and then the same battery with just 1 round bulb. And so I'd like to talk to you about what to expect in this. And one thing I predict is that when I add more bulbs in series, all of the bulbs are going to get dimmer. So I'm going to go ahead and starburst these bulbs, and I'd expect those are dimmer than this bulb right here. With just one, I'd think it's brighter, and then as you add more in series, that's going to make them dimmer. I'd also expect if I was doing arrow tails that I'd see a lot more charge flow or current in this circuit. As I add more bulbs in series, the rate of charge flow is reduced. We could see that by putting a compass under these wires, and we'd expect that it deflects a lot less. So this is all stuff that we'd expect and we should already know. The new thing I want to talk to you about today and also use to drive an equation is the color coding. And the idea of color coding is that we code the pressures, the electrical pressures in a circuit. So we've got this code that goes from highest electric pressure through normal through lowest electric pressure. And we know that since the battery pumps charge to that positive end, we'd expect the top of the battery to be the highest pressure, the red, and then any wire connected to any other wire has to be the same color, so that's all red. We'd expect the bottom of the battery, where it's missing charge, that negative side, to be the lowest electric pressure, and that'd be blue, and then any wire connected to any other wire has to be the same color, so that's blue down here. And then what I like to think of is I like to think in terms of steps and look at not the pressures, but the pressure difference. How different is the pressure from one side of the bulb to the other? So since it's red on one side and blue on the other, I'm going to count in terms of steps, and I'm going to count, and I'm going to say from red to blue, that's 1, 2, 3, 4 steps. There's a lot of pressure difference across that bulb. So that's why that bulb is really bright. I think of that pressure difference as that push that pushes the charge through the bulb. So that pressure difference across the bulb is the push that makes the charge go through it. Now when I come to this circuit, I know that the top of the battery is red, the bottom of the battery is blue. I also know that charge flows from higher to lower pressures, so my colors have to kind of drop until they land at blue here. I have to think what colors would make sense in each of those spots. And for me, I'm going to pick orange right here, yellow right in the middle there, and then green down here. And the reason I pick those colors is that if I think in steps, red to orange, that's 1 step, not a very bright bulb. Orange to yellow, that's 1 step, not a very bright bulb, but it's the same brightness as this one. Yellow to green, 1 step, same dim brightness as the other bulbs, and green to blue, 1 step, same dim brightness as those other bulbs. So that gets me the color code on there. Now I want to link to some terms and an equation. First of all, the idea of pressure, in formal words, electric pressure, is really called voltage, and we symbolize that with a capital V. But again, it's not so much about the pressure so much it is about the pressure difference. So way more often, instead of saying this is high pressure, this is low pressure, we may more often say, wow, there's a big difference across that bulb. So since we talk about pressure differences, we're going to talk more about voltage differences, or we're going to use this delta V symbol a lot more. And we've seen that we can measure this delta V, this pressure difference, with a voltmeter across different things in class. One of the other terms I want to look at is this idea of current, which we're going to symbolize capital I for current. We've measured that in class by putting compasses under wires and seeing how much the compass deflects, and we've also used ammeters in class to measure current. That's also called charge flow. Since current is how much charge flows past a place per second, it's measured in coulombs per second, or amps, or capital A, or amperes. Any of those are fine units. And then the last term that we're going to use in this equation is resistance, which is measured in ohms, or this horseshoe symbol also means ohms, as capital omega. So I want to put all of them together, and I want to think what could be an equation for current, for charge flow. And this equation has to make sense for all the circuits I've seen. It has to make sense that I have more charge flow here and less charge flow here. And what I want to think about is the thing that causes charge to flow through the bulbs is that pressure difference. More pressure difference for everything else being even, more charge flow. Less pressure difference for everything else being even, less charge flow. So I want to think the pressure difference is the cause. That must be like a direct relationship. The more pressure difference, the more voltage difference, the more current. But I also know that there's something else that matters too, and that something else is resistance. If there's more resistance, I might expect that for the same pressure difference, I'd have less charge flow. So it means it's going to go on the denominator. That is not a direct relationship. That's sort of an inverse thing there. And so what this law is called it's called Ohm's law. But for me, I like to really think about it way more conceptually. I like to think the pressure difference is the cause of the charge flowing. The resistance is the hindrance to charge flowing. We have to put both of them together to decide how much current or charge will flow through something. More pressure difference, more charge flow, everything else being equal. More resistance, less charge flow, everything else being equal.